we're almost at the top of 30 minutes into the hour. So Miguel, Pedro, and Bryan talking about performance engineering for the next hour. You guys ready?
Yeah, I think we're first going to start with Coil's update, which is Joran and Don. I don't know if you guys want to start sharing the screen, and then we'll switch to our screen share once they're done.
Cool.
Okay. Go ahead, Joran, Don.
Cool. Thanks, guys. Yeah. So we're just going to give an update on what we did last time. So at the last convening, we instrumented the central services stream library and the MySQL queries to generate the above waterfall chart. Just a reminder that the waterfall chart shows what is happening, when it happens, and for how long. So what you see here is a waterfall chart for the entire Mojaloop transfer. Where we ended last time was that there were gaps between the processing of the prepare and the notification, and the same thing for the fulfill and its notification. So we'd just like to share with you our findings. So if you remember, Mojaloop is made up of services that pass messages to each other through Kafka. More specifically, handlers are set up to consume from a partition and write to another one. So this is just an illustration of that. The horizontal axis represents time. The vertical axis illustrates when a handler is connected to a Kafka partition so that it can receive messages. So it's a step function because the handler is either connected or not. So there are two variables you can configure: consume timeout and recursive timeout. What's shown here is the case where there are no messages in the partition to consume. So the handler connects and waits for consume timeout before disconnecting, then waits for recursive timeout before connecting again. So this next image just shows what happens when a message is dropped into the partition. So the handler connects at T0, and then at T1, it receives a message from the partition. It then closes and processes the message for a time of C work. And then as soon as that's done, it then connects back to the partition. So it gets really interesting when you start connecting these handlers in series, and that's when the gaps begin to materialize. So in the simplified case, the top one would be like the prepare handler, or in this case, the combined prepare handler, and then the bottom one would be the notification. So as you can see, when the gaps materialize when the first handler writes to the partition when the second handler isn't connected. Right, so this isn't a bad thing. In fact, it's the key to high throughput. So one can amortize message overhead by batching messages. So instead of fetching a single message, one fetches a batch at a time. We modified some the consumers for the central ledger to take advantage of this. So firstly, we did two things. Firstly, they pull a batch of messages from Kafka, and then also they process them concurrently. And then we work closely with the core team to test and validate the changes. So the graphs here show the effect of scaling the number of handler instances, as well as increasing the concurrency within the handler. So that's just basically how many messages it processes at the same time. So the blue dots on the left graph is the baseline where the handler pulls just one message and processes it. The red dot is when it pulls two messages and processes them concurrently, and then the yellow one is when it does four. So the graph on the right is just the percentage improvement in TPS over the baseline, and we see by processing 4 at a time, we can increase throughput by roughly like 50 to 60%. So then the next thing we looked at was like the actual work done by the combined prepare and position handlers. So on the left, we have the SQL queries for the prepare leg, and on the right for the fulfill. The indentations show two things. The first is causal dependency, and the second is that the ones in the same indentation are being performed concurrently. So due to the current schema, we couldn't really optimize the queries any further without sacrificing auditing and safety. So just to illustrate the effect, the cost of an SQL query, we decided just to remove the duplicate checks. And when in doing so, we saw an improvement of about 16% in TPS. So the takeaway that we got from this was that there is a cost to be incurred by moving data to code and vice versa. So this led us to another insight. So currently it takes 13 milliseconds of work for one transfer spread across 18 DB queries. This left us with the question, what if we could do 4 milliseconds for 100 transfers all in one database query? So just to quickly sum up all our insights and lessons that we've learned along the way, is that two-phase commit balance tracking is a simple problem, but a hard bottleneck to get around with relational databases, even in-memory databases or stored procedures. So we didn't want to stop here and leave you guys all on a cliffhanger, so we took a stab at trying to solve this. Yeah, I'd just like to hand over to Joran.
Thanks, Don. So to solve the crux of the problem, we designed Tiger Beetle. Tiger Beetle is a purpose-built two-phase accounting database that we've wanted to do for a long time. And this is just an early preview of Tiger Beetle that we want to show you now. So it's something we've been building just the past 3 weeks as a surprise for the convening, a cherry on top, to take all our performance learnings this year, put them into practice in a purpose-built database designed from the ground up for prepares and fulfills. So why a purpose-built database? Two main reasons. We want more performance and we also want more safety. Firstly, we want more performance. We want to batch up all prepares and fulfills we receive in a 50 millisecond window and then send them all in a single network query to the database. This gives us low overhead networking, nice sequential disk write throughput, and amortized fsync. To make batching possible, we want the balance tracking logic to be in the database. And this is a huge paradigm shift. So we're moving the code to the data, not the data to the code. And it lets us avoid messy caching logic outside the database. We can keep the application layer really simple and completely stateless. Then this is just a quote from two recent papers that came out. The major availability breakdowns and performance anomalies we see in cloud environments tend to be caused by subtle underlying faults. So i.e. gray failure, slowly failing hardware, rather than fail-stop failure. So for example, disk and solid state RAIDs, they experience at least one slow drive 1 to 2% of the time, where slow means really slow compared to the median. So we want low latency to meet our SLAs. We want to use redundant nodes to mask transient gray failure performance problems. So if a disk write that normally takes 40 milliseconds suddenly starts taking 4 seconds because the disk is slowly failing, then we want to mask the gray failure automatically without the user seeing any 4-second latency spike. So we want more performance than a relational database, but why is more performance so important? So firstly, performance is not the need for speed. We don't just want to be fast to be fast. Performance is about reducing cost, the cost of deployment. So if you can make a system 1,000 times faster on the same hardware, then you can save money by deploying less hardware. Secondly, performance increases availability. If you can make a car that can do 100,000 RPM in the red, and then you only drive it at 10,000 RPM, then you've got a stable system and it's just going to work. Even if you're in a cloud environment and you've got noisy neighbors, you've got a really large margin for safety, for availability. And third, most importantly, why we want more performance is because if we can increase our power to weight ratio, if we can shrink a powerful system onto a small device, then suddenly developers can start running a whole Mojaloop stack on their home laptop. You can increase community engagement by making it easier for developers to get up and running with Mojaloop to start contributing. But more performance is not enough.
CSS, when people write like big CSS files and you use
We also want more safety. We want more safety than a relational database can provide, something like MySQL or an in-memory database like Redis. So it's not just strict consistency and crash safety. That's not enough safety. We also want to detect disk corruption. Just to give you an idea of how real disk corruption is, there's a whole lot of studies done. The number is about 3.45% almost every 3 years per disk. So when you start having 30 disks across deployments, your probability is going up to 100% in a 3-year period, where you'll be having balances corrupted, critical data corrupted. And that's a really hard problem to track down, to try and detect manually or fix manually. So we want the software to do this for us. We don't want to detect this when we do settlements. We want to detect it automatically and repair automatically without stressing out the operator. So the other thing where we want more safety is we don't want to trust the F-sync of a single disk like MySQL or Redis would do. We don't want to trust the hardware of a single node because disk firmware and operating systems, they often have broken F-sync. So we fixed a bug in Node where for years, Node's macOS F-sync was completely broken. It just flushed to the disk cache, but it never told the disk to flush all the way down to the platters. And you find those bugs in operating systems. There's another one actually in the new Apple macOS for certain combinations of file descriptor flags. So these problems are everywhere. They're in the Linux kernel. PostgreSQL had an F-sync problem for a long time. So, and apart from that, I mean, nodes just fail all the time. So we don't want to trust F-sync or a single node. So we want database to do synchronous quorum replication to at least 4 of 6 nodes. You could do also 2 of 3. It's configurable, but ideally 4 of 6. Another reason where we want more safety than MySQL is we don't want the risk of split brain. So it's easy to run a primary-secondary database pair, and then usually failover is done by the operator. It's a manual process. But there's just so many stories where that goes wrong and you get split brain and you get the data in 2 different states. And that can cause a multi-day outage. So we don't want the risk of split brain when you fail over. And then finally, you know, as some Mojaloop deployments start getting really, really big, we don't want to slow, we don't want really slow database migrations to impact customer uptime. So the nice thing about all this performance safety stuff that we're thinking of is it's really developer friendly. Because it's a purpose-built tool where we only had a general purpose tool like MySQL. Now we've got a tool that's meant for doing all the typical central ledger validation, balance tracking, persistence, replication. So it's really, really easy as a developer. All you have to do now, you don't have to try and make MySQL into an accounting database. You just have to send in a batch of prepares to Tiger Beetle. It's just a single hop on the network. And then you send in another batch of fulfills to Tiger Beetle and also a single network hop. So just 2 things, in prepares, in fulfills, and you can do, you can get on with the rest of what you want to do in your stack. So let's take a look at some actual numbers now. So at the top there, MySQL Mojaloop cluster, that's our baseline, and that's our minimum deployment. So what we did was across the whole cluster stack, we ran like 1 pod of ML API adapter, just 1 pod, and so on through, you know, for the different functions. And that cluster, on our reference hardware is getting 76 financial transactions per second. So 76 is the number. That's where we started from in March, April. Tiger Beetle is already doing 200,000 financial transactions per second. And these are directly comparable because you can see that the unit is FTPS. So it's not SQL queries per second anymore. It's actual 200,000 transfers per second. That's a prepare, that's the fulfill, and it's doing 200,000 of those a second. And this is just an early preview. So we actually then did a little bit of a heart transplant, and we integrated Tiger Beetle into Mojaloop, and we connected it at the ML API adapter layer. So 880 FTPS, that's just for one Node.js process, 1 pod, 1 container. It's running ML API adapter, and that's using the Tiger Beetle client library to collect batches and ship them off to Tiger Beetle, persist them, do everything. And it's getting 880 transfers per second. We found some bottlenecks though that were pretty interesting. It was in the node stack, it was in Happy, it was, so in the end we wrote something called Fast ML API adapter, and it does exactly the same as Mojaloop's current ML API adapter for the Happy path. It just uses nodes raw HTTP. And we could, with that, so just with a single node process, just one pod plus Tiger Beetle, and we could get 1,757 transfers per second. So again, yeah, that's per pod. And integrating was really easy. It was just 10 lines of code for the prepare HTTP request handler, another 10 lines for the fulfill. Everything is completely stateless. So if you need more than 1,700 with one container, you just spin up another one and you double that number until you get up to 200,000. So a lot of the stress and deployment issues are all solved. And we're just hoping to improve these numbers and also explore how we integrate with Mojaloop. So just finally, let's take a look at the architecture. So Tiger Beetle is LMAX plus quorum replication for performance and safety. So you may have heard of LMAX. They're a low latency trading architecture. The architecture is really simple, really friendly to the hardware. It's what the LMAX people call mechanical sympathy. And that's the guiding principle how Tiger Beetle can support such high throughput. So we're actively developing Tiger Beetle. This is just an early preview. We don't have more time to do a deep dive into all the design decisions, but we're looking forward to talking more with you at the next convening about Tiger Beetle. And in the meantime, you're welcome to join us on Discord and also to find out why we named it Tiger Beetle. But while we've been working on this, Tiger Beetle is a purpose-built accounting database to replace MySQL. Pedro and the rest of the team have been working on a POC to explore scalability within Mojaloop. So we'd now like to hand over to Pedro and the POC team.
Thanks, Joran. So let me start by sharing my screen. Let me know if you guys can see it.
Yeah,
we can. Mm-hmm.
Right. So my name is Pedro Barreto. I'm a solution architect at Crosslake, and this POC initiative is about anticipating the next level of scalability and performance and understanding how we can deliver it. So I'll quickly go through a few slides to recap the context. This is great timing, given the findings that our infrastructure colleagues shared earlier. So we think we actually have some ideas on how to fix this. So the motivation for the POC was to find an architectural design for the future, one that is cheap to start with and that can scale to handle more and more load with predictable small cost increases. The predictability and the small cost increases here is the driving force. So we're not trying to reinvent the wheel. Our objective is to investigate proven patterns and principles that can be applied to deliver the horizontal scalability, recognizing that the current shared database model might not be the way forward for the extreme scalability that we're after. Event-driven, we already have it in the current design. It means that we are communicating between services using asynchronous events, and we're not using direct communication between the services. CQRS fixes the mismatch of both the performance and the data structures that we typically see in complex systems. So most systems don't spend the same amount of time reading and writing, and they don't use the same data stores or structures for both ends. What ends up being is we have a compromise. Neither of the two scenarios is really optimal. That means that we are recognizing the differences and we're separating the application in two parts. The write side of the application that processes the commands and the read side that processes the queries, both being fully optimized. It also helps with edge computing. Should we need read optimized stores closer to the data consumer? So CQRS, I forgot to mention, stands for Command Query Responsibility Separation, segregation. Then we have another pattern, which is event sourcing. And this pattern helps addressing the fact that we cannot reliably or atomically update a database and publish messages to a queue at the same time. So it solves the problem by using the event messages as a way to store the state of the application. So this pattern goes really nice with CQRS, which means that for the right side of the application, so the part that typically struggles with high loads, we can keep the state of the application as a series of events. And this is similar to how database logs work. So, and on the other side, we create the read part asynchronously from those events at different speed. Of course, this POC exercise was time bounded, so only the happy path was in scope. However, one of the key guidelines was that the new design should maintain the same functional and non-functional requirements for everything. Obviously, that's not related to scalability. So in the end, a key deliverable was to share the learnings and to have a plan to apply this if and where advantageous. So just to recap the objectives, these are the SMART objectives that were defined at the beginning of this POC exercise. So we need a minimum deployment unit which is able to sustain 1,000 financial transactions per second, where 99% of it takes less than 1 second. And this needs to run for an hour of the test. And this needs to be a minimum hardware footprint, which is something that we need to come up with, which is what is that necessarily hardware footprint for that kind of performance. The second objective is related to the scalability, which is, can we increment the system in terms of resources in a way that the steps relate to the increased workload, so that we have that close to linear scalability that we're after, the horizontal scalability. So basically, we need to have an architecture that gives us that. Obviously, there's going to be a point, which we haven't found out, by the way. There's going to be a point where this horizontal scalability reaches its limit. So point number two, the objective number two, is to understand if we can create this design that lends itself to this horizontal scalability, where we increase cost in a small step to increase the performance. The third one is the demonstrated scaling performance, which is, can we achieve 5,000 FTPS, for example, with the same requirements of duration for the requests and the same test that runs for 1 hour, with 5 times the scale, which means if we have 5 times the amount of resources, can we have 5 times the amount of handling ability in terms of load? And this effectively proves that we are scaling horizontally. And the last objective, which is an optional objective, but it's a very interesting one, is to understand where does it break? As I mentioned before, there's limits to this horizontal scalability, right? And we are interested in knowing, where does it break? Can we keep on scaling it indefinitely? We're sure we cannot. So we need to understand, where is that? So we broke this into two milestones instead of going full bang. The first milestone was to test the scalability of a design according to the guiding principles. And the guiding principles were pure event-driven and microservice design that had no shared data between the parts of the system, where all of the central ledger components own and hide their own data and communicate exclusive by events, and 0 database transactions. And this is the part that has a slight change. The second milestone is to investigate other principles like CQRS, event sourcing, and these two in conjunction, they allow us to have that single write to Kafka that sends the message, that signal that something happened, so that the other part of the system can react. And it also carries the state of the application, so that we can have projections being made on the other side of the application with just that single write to Kafka. So these patterns have obvious advantages, but come with added complexity. The objective of the second milestone was to prototype them and understand if they are beneficial. So is the added complexity worth it in terms of added benefits? Regarding the state, we achieved milestone 1, mid-PI, so a few weeks back. Since then, we've been stress testing the system, and to get more load. And in parallel, we've been working on the event sourcing and CQRS implementation. So exactly what does this mean? What did we do? We started by splitting the transfers and the participants so that they can do their own things really well separated. And then we designed the whole transaction as a series of messages being passed between them. When we proceeded to the building of that more granular event-driven transaction flow, applying the single responsibility to the microservices and the participants and transfers, which are not aware of what the other part of the system is doing. And we tested it to see how well it performed. In the last weeks, we've been building the event sourcing and mechanisms, and we're now finishing the read side of the CQRS, the part that creates the projections. So this last part is in progress. How does this work? So this is the deployment diagram showing that the POC central ledger design with this new way of separating the services. You can see that we now have two services for the transfers with their own data store, and we have the same for the participants. They don't share data, they don't talk to each other. We can also see that the message flow to achieve the transaction is happening through Kafka and never through a shared database. So in a few minutes, Miguel will walk you through the full environment with a bit more detail. This is the sequence diagram. So I know it's a bit busy, it's difficult to read, but this will show the split between the transfers and the participants. This is a saga choreographed strategy where no part knows about the whole transaction, and all parts know how to react to events that happen on the outside and do their own thing. So we're at least this is the opposite of the orchestration strategy, where we have at least one component that knows how everything should work and makes decisions about what should happen next. In this design, what we have is small components. They know what they are listening to. They know that they listen to events that come from the outside, and they know what they have to do in their own piece of the world. So they are clueless about the rest. So this is only the happy path. This is a big and important mechanism. But we actually designed and accounted for the known failure modes just to see if we were not designing something that would not pass the test of reality. We just didn't build it. So to be clear, we did the same exercise for settlements with Michael and Neil to make sure that it integrates nicely. So we are now only showing this happy path, but we have other designs and other flows that show what happens and what do we need to do in terms of compensating events that can roll back whatever we have whenever something that is not the happy path works. So we designed for it, we just didn't build it. As you can see, we have the new services in yellow and green. So the ML API adapter, REST service, and the notification services are the same, with minor changes to accommodate the different topics and the new end-of-leg messages from the central ledger. So I'm now going to walk you through the prepare leg, and you can see that it all starts with the ML API adapter notification, receiving the transfer request post. At that moment, the ML API adapter sends the transfer prepare requested event to a special topic. That message gets interpreted by the transfer's event handler. And the purpose of an event handler in this design is just to react to things that happen on the outside, and if necessary, send a command to the other part of the transfers in this case, signaling that work needs to be done. So we are separating, one part is the part that decides, do I need to do something about this event that I just received? And the other part is, well, I'm actually going to do the work now. So the transfer event handler receives that event, and upon processing and some minor validation, creates a prepared transfer command. This gets obviously read or consumed by the transfers command handler, which will do validation of duplicates, creating the transfer with the proper state. And if everything goes well, at the end, it sends an event signaling that this was okay. And that is the transfer prepared accepted event. This event in turn gets picked up by the participant event handler. that will do the same logic. We'll say, well, I need to do something when this event happens, so I will create a command for the participants command handler to do the work. And I will send the reserve payer funds command. Then the next thing is that the participant command handler will interpret this command and work on it by validating the participants, checking the limits, and updating the position on the payer. So obviously the consequence of this work from the participant command handler is another event. So at that moment, if everything goes well, there is another event that the participant command handler sends, signaling that the payer funds were reserved. This is the other event. In turn, the transfers event handler is interested in this because it says, well, I'm almost there. So now I can send another command to the transfer signaling, well, you need to acknowledge that the funds were reserved. So this is all okay from the participant side. And remember, the transfers has no idea what happened on the participant side. So the only way for that part of the world to understand what happened is to receive those events and interpret them. So upon receiving that payer funds reserved event, the transfers event handler will send that acknowledge payer funds reserved command that will be processed by the transfer command handler as a signal everything is okay, which means I will update my state to reserved and I will send the final event of the prepare leg that in turn will be picked up by the notification handler and sent to the FSP. So this is how it works. I'm not going to bother you guys with the fulfill leg. It happens pretty much the same, obviously with different mechanisms. So I know what you're all thinking. This looks like a lot of back and forth. So it's going to take forever to complete a transaction in this way. But we have results, and Miguel is going to explain you how the environment works and how the results are the ones that we achieved. Miguel, take it away.
Thanks, Pedro. Just before we share this presentation, we'll just need to update the previous slide with a better resolution picture. We didn't realize it, but it looks pretty bad.
Apologies for that.
Okay, right. Okay, so I'm going to take you guys through basically the performance testing and the environment that we set up. So from the previous PI, we actually utilized the same environment. In that environment, we had two separated Kubernetes clusters, one specifically for JMeter, which had a master and a slave deployment pattern, and that means we could scale out the JMeters as much as we needed to meet whatever kind of throughput that we needed. And of course, then we have the actual main performance cluster, which included the Mojaloop components themselves. In this case, we used the ML API adapter. We did some slight modifications for it to talk the same kind of commands that we're now using, and also updated the notification handler to also listen to the commands that it needs to for the POC. And of course, we have those two new components, which is called the POC transfers and the POC participants. And we also have simulators that you'd expect. We've utilized the legacy simulators, but we've also implemented our own small lightweight POC simulator. And the reason for that is there was quite a bit of overhead at the moment by using the notification handler. There's some issues that need to be addressed there and some optimizations that need to be addressed there. So we took the notification handler out of the picture. And otherwise, in all purposes, we're doing exactly the same thing the notification would do without the HTTP traffic at the moment. So we're just measuring the core processing time per se. And if you could move to the next slide. Oh, also, we have the same versions of Kubernetes, the same version of Rancher, etc. So in essence, the environment is very much exactly the same of what was previously tested in previous PIs. If you could move to the next slide, please. So this is just a visual representation of how it was deployed. So we have the JMeter on the far left, we have the ML API adapter, and of course we have the individual topics in between the components. And you'll see that we have the transfer handler itself, which is divided into those subcomponents, the transfer event handler and the transfer command handler. So as part of the POC at the moment, we're deploying those components in one container or one pod, and they run as a discrete deployable artifact within the actual environment. It's not to say they can't run separated. We can deploy the event handler and the command handler as their own distinct components. But for the POC, we haven't seen the need to do it. And so at the moment, they deploy it as one deployment itself. And the same pattern is applied to the participant handler as well. And of course, I'm not going to take you through the exact flow because the flow was already shown by Pedro, but you can see it's following the same. If you look at the flow and you apply it here, you'll see it follows the exact same thing. Down below, you can see the simulator itself, which is receiving the final domain events. In other words, whether a transfer was prepared or was fulfilled, depending on the action itself. It either regenerates a new fulfill request if it was a transfer prepared, which will be then produced back into the ingress events topic, which is the same thing that you would expect from the notification handler calling the ML API. And then on top of that, it would also terminate the transfer if a transfer fulfilled event would occur. The other thing that we introduced is a metrics exporter. So at the bottom there, you'll see it's listening to the same events that the simulator is, and its job is purely just to basically process that and crunch the numbers in the transfer times and basically provide those metrics to Prometheus, which are obviously displayed via Grafana. And you'll see that we're also collecting metrics for Kafka, and we're also collecting metrics for the data stores on the far right, which is Redis. And as Pedro said, due to the way that the architecture is and the fact that we've separated the concerns, we now have distinct data stores depending on the particular use and the components that are being used. So for example, the transfer handler currently is attached to 2 data stores in this example. There's one specifically for persisting Redis, persisting transfers. In other words, this is how we store duplicates, and that's purely just storing the transfer IDs themselves. And then we have a second store, which is a cache, and that's storing the actual transfers themselves. And the idea being is since we have the CQRS pattern here, we are storing the transfers themselves in a temporary cache so we can deal with them for the in-flight processing of it. And of course, the later persistence of that will be handled by the query portion of the CQRS, which will be discussed a little bit later. And then the last one is the Redis participants store, and that's fully persisted at the moment, but it's also temporary because we haven't fully implemented the event sourcing portion of the POC. Once we do that, that store is no longer needed. It's also worth mentioning that depending on how we implement the duplicate checks, at the moment, as I said, we're just storing the transfer IDs themselves. If in future we move to something like a Bloom filter, we could also remove the duplicate Redis persistence store as well, since we can handle the processing of those duplicates in memory by using something like a Bloom filter. Also on the far left, you will see the components that we use for the deployment. So there will be a bit more in terms of why we chose some of that hardware and the lessons learned, but you'll see that the ML API, the simulators and the transfer handlers, participant handlers, etc., are running now on C5 instances on AWS. We're still using super fast storage for Redis on the i3s, and we've moved Kafka and Zookeeper to R5s, which are memory optimized instances. And at the bottom left, you can also see just a summary of the metrics, or some of the metrics that we're exporting. So we're basically capturing the operations per second and the processing times of the end-to-end financial transfer itself, which is including the prepare and the fulfill legs. We're also capturing metrics for just the prepare leg and just the fulfill leg. And of course, we're capturing the metrics for each of those individual components, the event handlers, the command handlers, and we're able to basically see or visualize how many operations per second they are doing, as well as how long they're taking to do the processing as well. And also, just once again, there is a complete separation of data here. The participants doesn't care about the transfers from a data perspective. All it cares about is handling the events that it receives. And of course, it has the information it needs in those events to do any kind of action from a transfer perspective. And of course, it accesses its store to get any information it needs from, for example, its participants, etc. I think that's it. Maybe next slide. Right, so I'll take you through two performance runs. Well, I think you skipped one. Yeah, sorry. First is when we scaled for 8 FSBs. So we basically determined the minimum hardware that we, well, based on our time constraints, that we needed to run 8 FSBs. And you can see here, we got some pretty decent figures. In general, we have the main indicators, which are bottom left. In other words, we need to achieve more than 200 financial transactions per second. We achieved 1,002 financial transactions per second. And once again, that includes the prepares and the fulfills. And of course, we need to do that with a sustained for an hour run. We have achieved that. We generally do our runs for 80 minutes. In this example, I've just taken a snapshot of an 80-minute run, just an hour portion of it. And the other key indicator is we need to make sure that 99% of our transactions, our financial transactions, are basically below 1 second from a latency perspective. And we have achieved that. In fact, you can see that the average response time for the full financial transaction end to end is 65 milliseconds, which is pretty impressive. And of course, the fact that only 0.03% of the transactions were above a second is also an absolutely great result. I think that's also worth mentioning, that it was quite a big surprise about the latency, because inevitably, as Pedro said, we expected to potentially see a higher latency than what we currently have in the current code base, because of all the hops that you can see. So it's a lot more chatty than what we currently have. And in fact, in the last PI, we did work on actually combining some of the handlers into a single handler to reduce those hops, to see if we could get better performance. And here we've actually done the opposite, and we still achieved, surprisingly, a much better response time than we could have actually imagined.
This is really awesome. Can I ask a quick question, though? Did you guys look also at the work that was going on in parallel that Don talked about with and Joran, when they were talking about batching in and out of Kafka?
So we have not spent time on that. You'll see on one of the slides a bit later on. That's something else that we can look at. What we did do is we did, from a Kafka library perspective, spend time optimizing and tweaking the batching from the underlying client's perspective. So in essence, the client Kafka library itself is doing batching for us.
Oh, I see. Okay. That's one way to go at it for sure. Just hide it inside. The other would be to say it's actually, the batching may only be needed at ingress and egress at the edge where it goes in and out of the API adapter, so that you can handle the offloading of that adapter into the eventing pattern as quickly as possible, but then use discrete events throughout the system for the ease of implementation.
Yeah, and that's currently how the Kafka underlying Kafka library works, right? It's basically, it's buffering, collecting a whole bunch of messages or consuming them in basically chunks at a time. And even when you produce the messages, it will try chunk them into batches before it's sending them and writing them to Kafka as well. So
okay, that's great. Thank you.
Tweak that, and we believe we've tweaked that quite well to work with how this current architecture is working. Not to say that we still can't maybe batch it for the processing of positions and things like that. That's certainly a possibility. But of course, it's also worth mentioning there's obviously a balance, right? The more you're going to batch, the higher latencies you're probably going to see. You might get more throughput, etc. But there's going to be a give and take by either, going with more discrete individual transactions versus bigger batches.
It makes sense. And is there was another panel chat question here about the restart, since you're looking at in-memory caching using Redis for performance reasons. And while it might be persistent at present, the participants is looking to move to an in-memory only snapshot for positions, which suggests then you have to restart. At some point, you'll have to rebuild the in-memory version of Precision from something else. whatever that is. Has that been looked at yet? So you have maybe you could explain that setup there, Pedro. I don't know if you want to talk about that.
Well, yes, we have two stages. The stage that we have now, which is just the event driven with the half of the CQRS, takes care of that by using Redis as a full storage mechanism, which means we process everything in memory. Well, first, let me start with another thing. The way we have the partitioning guarantees that position updates for a certain participant always end up in the same instance of the application. So this is a guarantee that it's important for the rest of it. And then what happens is that we load the state when that instance starts. And then we process all of the commands in sequence, which guarantees that the position updates are consistent. Every time that we process a position update today with the event sourcing mechanism, previous or before the, sorry, with the event driven before the event sourcing, what we do is we do the updating memory, but then we send an update to Redis. So we make sure that we are keeping Redis updated and consistent always. Obviously that has a small performance hit, but we'll discuss that in the next slide. So the way it works today is, yes, we are keeping the store, we process in memory, but as soon as we process, we make sure we update Redis before going back. In the future, what we want to do, and this is the code of the event sourcing that we have already, is we don't wait for Redis. Actually, we just update Redis after responding for the, just to have a cache. So basically, we do all of the processing in memory. We do all of the updates by using state changes with the messages, and that achieves a better performance. We don't have that yet. It's not tested.
Yeah. And it's also worth mentioning that, of course, it doesn't matter if it fails writing to Redis, because inevitably what's going to happen as well is, due to the event sourcing as well, it's going to go and also fetch the state from the snapshots, etc. So it's going to rebuild its memory from a combination of those sources. But I would say definitely the most important source is going to be the snapshots. They get written back to Kafka.
So the important message there is that in this model, there's a single thing, but participant handler per participant. So everything is guaranteed to be processed in order, and can, if that thing died and needed to restart, it just needs a stream to recover from and a snapshot to expedite that. But you're guaranteed that the same order of events would come back into it. And then all you're eventually concerned with is its memory state. For the position, Redis becomes essentially a snapshotting mechanism, but it's not required.
Exactly. So basically we have an approach where we have three mechanisms. Each of them are executed in sequence. The first ones are faster. The last ones take longer, but are more consistent and give us the guarantees. So when we're loading something with the event sourcing, the first thing we try is cache. If cache is not there, then we try to go for the snapshots, which is a special event that has the last state of a given entity. And then after the snapshot, we apply all of the events following. If we don't have a snapshot, then we revert to applying all of the events in sequence. This is pretty similar to how SQL databases work when they have transaction log enabled, which is the performance mode, which is there's a snapshot that has the current state. And then what happens is that we keep writing operations one after the other one, and the resulting state is only achieved when you apply all of those things in sequence. So it's pretty much the same thing.
It's also worth mentioning that it actually might be a combination of those. So for example, for participants, which is a very small amount of data, relatively speaking, right? Because you would only, I don't know, maybe you only have 200 FSPs within a system or something like that. So I don't, in that case, it may be necessary that we actually don't need a Redis cache, because it's actually very quick to load those states from the snapshots directly. So we haven't got there yet, but it's something that we need to look at. But things like transfers, which is a lot of data, that would make sense to use a cache and not always load it from the actual snapshots, etc.
Exactly.
That's great. Thanks. Great summary. We should let you continue, I guess, but thank you.
Okay, yeah. So the other thing that's on here, you can see the number of containers. So we ran about 71 containers. So as Bryan said, we have a dedicated participant handler for each FSP. That's why you see 8 here. And we found that the ratio from a scaling perspective is the other components like transfers, etc., would generally be 3 times however many participants we have. That seems to be a good ratio that we found. And below here, you can see on how much hardware that we ran on. So we had basically 14 machines that we ran on. Once again, you can refer to the previous slide to determine the exact types of machines that we used. The only thing over here, we deployed 5 Kafkas on 5 machines. Zookeeper, we only had 3, but they were deployed on the same machines as Kafka. We wanted to be kind of consistent there. Right, moving to the next slide. So next run we did was 16 FSBs. And we also got a pretty good result here. Whoa, too many slides, go back. Yeah, so looking at our main indicators, we achieved basically from a financial transaction per second, sitting at a nice 1,900 financial transactions per second, which is pretty nice. Basically, we're seeing by doubling the FSBs, and also on the far right, you'll see that we actually pretty much doubled the hardware from 14 to 28. We have a bit more of an increase in containers because of that ratio, basically as well. I said, for every participant, you're basically going to have 3 of transfer handlers, etc. In essence, that means we are pretty much getting near, sorry, what's the word I'm looking for? Near linear scalability as a result of that. And the other great thing is if you look at the average response time, sorry, I don't know what's going on.
Apologies.
My Pedro projector has broken down.
Yeah, sorry, is this working now?
Yeah.
All right,
Thank
let me
you.
just open
Yeah,
my
it looks
notes.
okay.
Apologies, I still need another one. Zoom is just making it so slow. Okay, sorry guys.
Okay, so one other great thing we see here is actually the average response times here are sitting at 73 milliseconds, which you see is very close to what we saw before. So basically by doubling the hardware, doubling the FSBs, we are literally getting near linear scalability with a little bit of overhead that's being introduced. And of course,
I think the thing that's worth bringing in though, Miguel, here is that it's not so much that you're doubling the hardware, it's that you are applying hardware to additional DFSPs in a linear fashion. Correct. This is exactly my point about a unit of scale. That is, if I have to add 1 DFSP, what hardware do I have to add to the system, and what's the cost of that hardware? Obviously, you may decide that there's a group of hardware that can handle groups of 5 DFSPs, for example. I'm not saying that it has to be 1 for 1, but there's a way of saying, if I add a DFSP, there is a fractional hardware addition that I have to add, and that cost of that is less than it would have cost me to put the system up in the first place. And you're showing that the unit of scale here is very nearly linear. So I think with some additional work as you get to this, you may get to a point where it's actually sublinear. You're awfully close to this. So this looks pretty good.
Yeah, totally agree. And yeah, and also the transactions above a second was 0.13%. So yeah, still pretty good. I think next slide. Cool. Okay, so obviously Pedro took you through the 3 objectives earlier. So the question is, how do we basically rank ourselves against those objectives? For the first one, for the minimum deployments, as Miller said, we've basically been able to show that if we define a unit of let's say usage per FSP, and if we're able to scale that appropriately, we can see that we are getting basically a sublinear increase in performance. So from number 1 perspective, we've done that. We've achieved the 1000 TPS on a more or less minimum hardware footprint. It's worth mentioning that there still is some optimizations that we can do. You'll see in learnings later on that we have chosen different kinds of hardware. And we think we can further improve that as well, specifically around on the nodes that Kafka are sitting on and the type of hardware that's being used for their processing. So I think we're in a good place there. From 2, we can see from 8 to 16, we have definitely achieved a sublinear or near sublinear scaling. And for 3, so that one we're still busy doing some work on. We've just recently, I would say in the last 2-3 days, had the opportunity to try scale up to 32 FSBs. We are getting around about 2,700 financial transactions per second, but we're still playing around with some of the actual underlying supporting systems. So in other words, we're reaching a point where now we're having problems with with Kubernetes. So for example, we have to increase the number of ingress controllers. And also on the JMeter side, we've had to also do some tweaking on the JMeter side to be able to sustain those kind of TPSs. So we're in a great position at the moment where we're actually like, oh, our stuff's actually doing really well, but the other stuff that's running it is having problems, and we're trying to basically ensure that the underlying infrastructure can maintain that. So we're not there yet, but we're in a very good place to do it. And on top of that, when we introduce the full event sourcing code, since we have, well, the code is there, we just haven't had an opportunity to fully test it and work out 1 or 2 bugs, etc. We believe we'll definitely be in a much better place to be able to achieve the 5,000 financial transactions per second.
And on point 4 here, I want to make the observation that so far you've been adding DFSPs with all adding the same unit load to the system in order to demonstrate how the system can augment itself as you need to onboard new DFSPs. But there's a separate question, which is the verticality of this. If a DFSP starts to add to its own unit load, but you don't add new DFSPs, now what happens? So if we go beyond 100 TPS per DFSP or whatever the number is, then it goes to 200 TPS for that same DFSP. Now what happens? Obviously, one quick way that you can factor it if you find a problem is to create a virtual DFSP and to start, as we've said before, dividing its liquidity among multiple virtual participants so that you have the ability to process at the scale level that you're comfortable with. But there is a way in which to address number 4, where you can push the system through a set number of DFSPs to where it hits the fail point and say, what did it take to actually ram through enough transactions through, say, if you get to a point of 32 DFSPs, what is the unit load per DFSP that was required in order to push this thing past 1 second? It may not be exactly the same, but it gets us to a question about peak factor when one of the DFSPs starts really ramming on the system heavily and the other ones are sort of sitting at their normal rates. It's only one aspect of this, so I completely I have to give you on the point that it's a moving target and we'll have to keep thinking about it and how we characterize it. But this is looking like it's pretty good. I mean, it's looked like you're on track towards all of the goals.
And it's also worth mentioning that it's also a moving target because we're still in the process of introducing the event sourcing stuff as well. So we expect that to also impact in terms of how the system reacts and operates, etc. So yeah, agreed. Yeah, next slide. Okay, so just having a closer look at the scalability. So kind of maybe touching on something that you just said on the previous slide, Miller, is that if by observing what we have, we generally are seeing about 240 operations per second per participant. And of course, the caveat here, this is based on a C5 extra large instance. And of course, the participants are doing the prepares and the fulfills. So that actually equates to 120 financial transactions per second per participant. And therefore we can do this calculation where we can see with 4 FSBs, we theoretically hit a limit of 480 financial transactions per second. With 8, we hit 960. And obviously that's really good because we're kind of hitting 1,000 pretty much on the dot with 8 FSBs as you saw on the previous slides. And of course with 16 FSBs, we should be hitting around 1,920, and we're pretty much just 20 FTPs away from that, since we're sitting at 1,900 for just over 1,900. So it's looking like we are pretty much matching this model that we see here, which is a really good place to be. It's also then worth mentioning, well, how can we go or do better? Because I think we should be trying to do better without a doubt. So, and obviously from a improving things perspective, we want to focus more on the horizontal scalability of the solution. So this list is very much focused on that. So you can see for, well, one, we can do the event sourcing. Since we're going to reduce the dependency on Redis, we believe this will definitely improve things. Two is the virtual positions. So in other words, we are now, instead of having one participant handler that handles one specific FSP's calculations, we can shard the position through different participant handlers by setting up virtual positions. And therefore we're spreading the load, and we can obviously optimize that and process, in theory, more transactions per second for each FSP as a result of that. And three is also the batching. So also potentially, as I said, we are doing batching on the underlying Kafka libraries, but also trying to see what happens if we do batching by actually doing the calculations in a distinct batch. And the nice thing is the current architecture that we have at the moment, since we have buckets that are specifically designated for each participant, it's really easy to pick up a batch of 100 messages, just add all those positions together, and basically do one single atomic update operation to say, hey, here's the new position based on all these transfers, position changes for those transfers.
As you start thinking about number two, the virtual positions, there's a couple of different forks you could take. One is to think about what is the extra complexity that we will take on with what we'll call virtual the rebalancing of liquidity. That is the ability to take what is a single pile of money committed by a legal entity for the purposes of settlement and dividing the amount of that money that's available to each one of the virtual event handlers, that participant handlers that can then transact that. You'll very quickly find that the positions are going to run against you in one of those virtuals, and it'll run for you in the others. You'll then need an ability to rebalance. If you go down the second path of this, you could say, I'm actually not going to ever do that. I'm not going to care about it. I'm going to do something like Kafka does, which is the only time I ever consider this is when I add or remove virtual participants. And what then you can do is say, if I run into a position liquidity problem with one of my handlers, then I can simply remove it from the system. And that forces a rebalancing among the remaining ones. So in essence, you're saying I never have to solve the problem. I only have to solve one problem, which is anytime I take my full liquidity position and divide it equally among the available handlers is the only problem that I have to solve. And I make that as fast as absolutely possible. Because of course, all of the virtual participants go offline during that time at which you're doing that. Or they are suspended, I should say, more likely, unless you come up with a clever way to do that.
The virtual position thing. So in this model, they pushed up the per DFSP limit or capacity on this particular hardware to 120, which is a massive amount of sustained load from a single participant in the scheme. Faster CPUs would drive that up. More batching would make that a bit better. You know, it's more, if it was ever a problem, the same technique we've talked about for the existing system, virtual positions, could still be applied, I think is what they mean. But I don't think anybody's proposing that we invest development effort into virtual positions quite yet.
I think that's right. If you complete this work on the POC, and we're at a point where we adopt it as a community and then take on the work to actually implement this fully within the system, a second POC could then be looked at as to how do we deal with the case of starving a virtual participant capacity and saying how would we then introduce that. That's a separate work then on a stable architectural base instead of trying to deal with those two things at the same time. It makes sense, Bryan.
Yeah, and Miguel's about to cover point 4, which is, you know, faster hardware, but I was just going to kind of be clear about it, because you know, in this design to, you know, optimizing for in-memory for the real-time portion of the flow, then to get certain guarantees from the system, there has been a single threading of position management with respect to a DFSP. That's why now you'll see Adding more cores doesn't benefit a DFSP, but adding faster cores does. And so then there's potentially just other hardware footprints that have faster CPUs and less other resources, might be cheaper, but would scale you vertically for a DFSP.
Sorry guys, we're running out of, I think we ran out of time, so I think we need to really quickly scoot through this very, very quickly. I would like to get at least to the conclusion very quickly. So yeah, performance, I think we covered this already for 1065 for 16 FSP, 73 milliseconds with 9900. And we need to then do more work in terms of what happens when we do 32, etc. Right, so we've definitely achieved better performance. From a hardware perspective, it's actually, it's a pretty good story, I think, compared to what we ran on the previous PIs. This is definitely 3 to 4 times cheaper, and we're definitely doing much better performance than what we saw previously. It's worth mentioning that we were doing 387 milliseconds at equivalent 900 financial transactions per second on the previous PI performance tests. Cool, go next, please.
Should we skip these?
Yeah, I think skip this. This is just the detail. You guys are welcome to look at it. There's links on the calculations. Yeah, I think skip, please. It's just
right.
detail.
So
yeah.
Picking up and really quickly wrapping up, these are impressive numbers, but what did we learn from it? So the single responsibility principle not only increased scalability, it also simplifies the code. So now we have clear boundaries on the code, and we understand how the system scales, which gives us that predictability in terms of how much it's going to cost to have more load. And we still have more options because we have those different models to scale the transfers, which we are able to scale indefinitely, well, almost. And then we are associated to that limit of like that speed limit of the participants that Miguel and Bryan alluded to. So the other one is there's no news regarding TypeScript, right? So type safety helps. Number 3, because we have nice abstractions for the infrastructure, we were able to quickly test multiple Node.js Kafka libraries. And we now understand them much better. RD Kafka is the clear winner, so there's no contest. And besides that, we actually understand a lot more about the batching mechanisms, the settings, so we're in a much better position. Compression, we enabled it. It works. We need to understand it better. We might not need it everywhere. There are some places where small messages might benefit from no compression, but we don't know. Monorepo, this is something that we used for this one to speed up things. In the future, we may consider organizing the repositories around functional domains. So one repository for the transfers, one repository for the participants, another one for the infrastructure code, another one for the common stuff. We need to understand what is the right balance. Domain-driven design, tactical patterns around entities, aggregates, repositories. These patterns and these learnings helped us separate the code in a way that we can extend it and replace infrastructure implementation. So these are very good advice. Manual assignment of partitions to participants. We found this was a very simple implementation that achieved optimum distribution of the partitions, of the participants with the partitions. I always mix those two. We have obviously to incorporate that in the participant creation logic, which means a small update to the admin UI and to the API. But essentially what we have here is we have limited and we don't change participants that much. So there is no big problem in having manual attribution or assignment of the partitions to a participant. So what we can do better, we identified a few things. So knowing that the scalability limit with this design is the number of participant positions, we can further scale it by implementing virtual positions for each participant, as we discussed. Better hardware also helps, but we felt that this is kind of cheating because the purpose was to achieve horizontal scalability. In the current POC implementation, the participant services take care of the participant metadata and the position. We can further separate these two to achieve better performance. So one set of services just for the metadata of the participant, and then which changes very infrequently. It almost never changes for the time span of requests. And then the other part, which is just for the position, which is the one that's constantly being hit. Obviously, in terms of hardware, we discovered that we don't need certain optimized instances. General computing instances in the latest generation optimized C5s are actually better for most of what we have. So there's plenty of improvement space there. And the last one, which is not trivial, is the duplicate store that we are using for the transfer ID, for the checking of, is this transfer a duplicate? We can optimize this further. So we can use a Bloom filter like Miguel mentioned, because we are now in 1 hour getting closer to, with 2,000 operations per second, getting closer to 2 gigabytes of data with the normal duplicate check that we have. So by using a Bloom filter, we'll be able to optimize this to a great extent. So what are our conclusions? Separating responsibilities in the data stores delivers the desired horizontal scalability. We achieved this. The separation of the transfer and the participants provide data store partitioning, which is something that was desired and considered before without extra effort. So it comes by design with this architecture. The coded integration examples that we have with the settlements exercise that we did with Michael, it feels like this way of doing things and integrating to the usage of the events and the state events actually works. By using event-driven CQRS and event sourcing, we effectively are shifting the load to Kafka, which is much better at scaling horizontally than a database. Even if we factor in Kafka replication, it's much more efficient than most databases like the ones we're using, which are schema-based databases. Obviously, one of the objectives of this was to make the central ledger design retrofittable. We don't want to come up with something that needs a complete redesign of everything else. We're just focusing on the central ledger. And we can confirm that this is possible. So basically, and we can discuss this later, but the strategy is that with some bootstrapping mechanism to get the data that we have in the current databases to the new system way of storing the data. And then by having some handlers keep on updating the read view of the data that we have today in SQL, we can just plug in the new central ledger without much effort, and it will work. So what are the next steps? In here, what we did was we designed options so that a decision can be made. Option one is to incorporate the learnings to the current central ledger, which means we don't fundamentally change the code. We just cherry pick what we need to improve, and we put that to the current code base. Obviously, the pros is that we can cherry pick that minimum change. The other side of the coin of this is that we are unlikely to deliver the full benefit. And another pro of this approach is that, well, pretty much everything is there, right? The deploy pipelines, everything is set up already, so we don't need to rebuild it. On the other side, we may end up having a mix of standard JavaScript and TypeScript. This is no big deal, but it's not desirable. It does miss the opportunity to simplify the code, which is something that we keep on doing, right? We keep using the same code bases and increasing add functionality, which eventually will lead to some technical depth. So we miss the opportunity to fix that in a fundamental way. And then to incorporate a significant part of the learnings, it might even take longer than the rewrite that the other options advocate for. So, and also at the end, depending on which design principles to apply, a large refactor of code might be required, which is a risky business. So then we have option two, which is we make the POC code production ready and replace the central ledger with it. And this approach is the simple event-driven plus CQRS approach. So we have the pros single responsibility principle, the separation that we have alluded to. The CQRS read and write separation means that we can have as many views as we want in an asynchronous manner without having a performance hit on the transactional part. Obviously, TypeScript provides a benefit. The code structure, as we mentioned, provides nice abstraction and mechanisms to reduce technical depth going forward as we add more features on it. The granular events enable future asynchronous integration for settlements, auditing, fraud detection mechanisms, and any other real-time or manual decisions that you want to plug in, because it all works with events, and which means that we can send an event and wait for an event back before proceeding with the next step. We can put things in the middle, as well as process things asynchronously, like AI mechanisms, fraud detection, whatever. Obviously, there's a fundamental and a big con, which is distributed transaction architecture, which is what we have, is a complex business. It's much more complex than having a ACID DB-centric transaction. So it is more complex. It's more complex to build. It's more complex to debug. It's more complex to run. It is what it is. It requires better monitoring tools to fully understand how the system is behaving. Again, this is a drawback of this design. It's inevitable. And it still needs to update a local store and the queue. So it's not a single atomic write that provides that additional scalability and performance. So this is specific of option 2, and this is something that we can solve with option 3. Option 3 is the full bang, is the full event sourcing with event-driven and the CQRS. So the pros are exactly the same as option 2, but we introduced a single atomic write to Kafka that provides that extra scalability, performance, and performance. We have an extra benefit from this mechanism, which is we can now have effortlessly synchronization for a passive in-sync geo-replication. And this is something that we discussed in the previous sessions. We can have Kafka using Mirror Maker technology, which is a Kafka open source tool that replicates the topics that contain the state changes in the snapshots to the other side, to the other geographic location. And the other side is applying those constantly, which means that the other side is kind of an active cluster that's not serving, but it's updating its view, which means it has read side handlers to update the read side of it. And we can shift from one cluster to the other cluster fairly simple. And this is typically faster than the time it takes for us to manually do the switch from one side to the other. So this is an interesting aspect that we can explore. So the cons are pretty much the same from option 2. Complex, it's more complex than a DB-centric transaction. It requires better monitoring tools, obviously. And there's an additional complexity to option 2, which is due to the fact that we're loading the state on the right side from snapshots plus events and keeping the offset. So this is added complexity that is necessary to unlock that extra benefit of scalability and performance.
Pedro, before you finish up here on that one slide, on that last point, it may be worth engaging with the Confluent guys. There was a change that Kafka took from, I don't remember exactly what version, but they used to keep the core offsets that by consumer in Zookeeper, and then they moved to having those now being kept in the brokers. And it may be interesting to understand why did they make that change? Because I would have argued without knowing that they've done that Zookeeper is exactly the right tool for this. You can put the snapshot there and you can put the offsets there. And when a consumer comes online, it just reads the data. It's almost instantaneous to restart. And then of course it can, from the offset, roll forward on the event stream from there, just as it would normally be processing. So yeah, there's extra complexity, but not different from what you'd normally be doing on an event-driven startup where you have to read your baseline and then roll forward from there. And not different, I don't think, from option 2 really on that respect. But the question becomes, yes, but where did I get my snapshot from? And where did I get my offsets from? So if you have the ability to write a core snapshot without necessarily encoding it as an in-channel message that's in Kafka, but actually recording it somewhere as a snapshot that's part of the Kafka infrastructure, so it can be seen in line with the events, in transaction order, the events. That may be simpler. So I think it might be worth talking to the Confluent guys about why did they make the change from using Zookeeper.
We're actually using that mechanism. So from Kafka 0.5 onwards, the offsets of all consumers are being stored in the brokers and not in Zookeeper. So you're right. This is the offsets that we need to store, that we don't need to store. These offsets are the offsets so that we can cache and, so, let me start again. When we need to load from an event source mechanism, we need to find the latest snapshot and then apply all of the events afterwards. To find the snapshot, we can have a mechanism that makes it faster, which is if we have a cache mechanism of caching with Redis, for example, the offset of that snapshot for a given entity ID, so for a given position ID, we then can go to Redis, get that offset, and when we go to Kafka, instead of saying, go read all of the snapshots and find me the last one for that entity, you ask for just one, which is much faster. So again, this is a strategy that we can use to optimize the load, but we don't need it. So what I mean by this is, if that offset is not there in Redis, that's fine. We just read it all again. And this is no problem because we're reading it at the startup of the application. So, but you're right. This is something that we can investigate, and especially the mirror maker technology and the way to replicate to another geo cluster is something that we probably need to check with Confluent guys. So, what all of this and what is the recommendation? So we recommend that we go for option 3 during PI 11, and this is the full event sourcing plus CQRS mechanism. We do need to finish testing the event sourcing code. It's there, it's not fully tested, so we need to understand fully how it works. And if we don't get, or we don't care about the additional benefits, we can fall back to option 2, which is already proving to be very nice in terms of scalability and performance. So this is the recommendation from the team. What does this mean? So we need stuff to make it work. So currently we have the event driven on the right side of the CQRS working and tested. The event sourcing code is working, but we need to test it properly and execute some load tests. We also need to finish the read side handlers, which are fairly simple and don't impact the transactions. So we left it for last. And all of these tasks are pretty much either done or almost completed. So this part is fairly quick. We also still want to achieve the 5,000 FTPS. So we need to continue the load test. Then we have to spend some time making this code production ready. And this is the bulk of the work on the plan. So what we have designed is the flow with failure modes besides the happy path, but we didn't build those. So we need to build those parts, strengthen the code, and make sure we have better tests, more tests, better monitoring, etc. So all of this takes some time and some effort. And finally, we need to create the bootstrapping and the migration mechanism that I mentioned before. So what it takes, unfortunately, we haven't said a single time about timelines, of course, because this all depends on the chosen option. The resources available and whatever work streams drain resources from PI 11, so we don't know. What we do know is that we think that with a dedicated team, not knowing what exactly that is, we're assuming bigger than the one that we had, with a dedicated team, we can already, and picking up on where we left from the code that we have now, we can deliver this during PI 11. Of course, this needs detailed planning. So going forward, we need a decision and a detailed plan reflecting this decision. Finally, but not the least important thing, I'd like to thank all the team for the dedication and the commitment. This was very intense exercise performed by a small team. So kudos to the team. This was amazing work by everyone.
I'm going to second that. This is fantastic. Thank you very much. It looks like this is exactly what we were hoping to get from this round out. There is one thing more though, Pedro, that I'm going to have to add to your plate, which is the resource planning, of course, is essential to making sure the work can be done in PI 11. And so I don't want to take your attention away from that, because getting the work done, of course, is important. But the third item that we've talked about before is what will be the migration strategy for existing deployers to take this on? What will they be expected to do in their environment? Is it simply you start using the new central ledger and you won't notice a difference to anything else because it's infrastructure as configuration, or as infrastructure as code? It will simply redeploy and you'll have the right resources that you need, subject to, of course, the hardware limitations that are required. Or is there something more that they have to do, such as database migration or something else, which they'll have to then plan for, and that will have a specific cost associated with that for them to then adopt this change. Something that we have to, I think, study as we go into this, because of course, building it and no one uses it doesn't help us so much.
Yes. Yeah, that's a very good point. We know, obviously, we don't have the right number in terms of how long it takes to build those things. But what we know is that this system that we've built is retrofittable in the sense that we can plug it in place of the other central ledger code. Obviously, it's not just like that. So there's a bootstrapping mechanism, which means we need to run some scripts to get the data from the current data stores into the new data stores of this code. And we have to do another part, which is keep on updating the data store that today is being read from the other parts of the system that are not the central ledger, which means that there's a bit of a migration work to do. Effectively, what we think, and we gave it some thought, is that this is retrofittable. So there's some amount of work to do that. We think we can automate all of that work. I'm talking about the bootstrapping and the migration of data. Obviously, the infrastructure stuff is hard work. But once the infrastructure is done, we think we can automatically bootstrap the data, automatically migrate the data, and we should provide those mechanisms or those scripts.
Simeon, just wanted to thank you very much. Thanks, Pedro, Miguel, Miller. It was good.
Sorry, this was pretty late.
Special thanks to Simeon for allowing us to go 25 minutes over the time. But we want to highlight this again in the roadmap, I think, breakout discussions, because a lot of things that we want to look at will depend on the option that we take here out of the three. So thank you.
Thanks,
I appreciate that. I just want to pass it off to Miguel, see if you've got any last comments.
No, thank you very much, everyone. Thanks, Pedro. Thanks, Roman. Thanks, Don. Thanks very much for everyone. And thanks
everyone.
Thank you.
There's a lively discussion on the performance engineering going on Discourse. So if you want to hop on there, there's a couple of questions that you can respond to there. We're about 25 minutes over our time, so I'll pass this on quickly to Don to take us through the web payments presentation. Hopefully we can catch up with time before the end of the day. Don?
Cool, thanks, Simon. Simon, could I just ask you to add Adrian to the panelist group? Because he'll also just be...
Yeah, sure, I shall do that.
Yeah, so just some background. So the demo that we want to show you today pulls together a few technologies. Firstly, web payments, the web payments API, the mobile money API that you've seen from the GSMA guys. I just want to say thanks to Bruno and VG from the GSMA Interrupt Lab. They've been really helpful in helping putting this together. And then lastly, but not least, the Mojaloop stack. Yeah. So I just want to hand over to Adi, who will continue with the intro.
Thanks, Don. Sorry, folks, I just dropped off another call, actually the web payments working group call. So as we mentioned previously, there's a bunch of work happening at W3C to develop a set of browser APIs for payments. So basically building payments more natively into browsers. It's an ongoing effort, and the implementation status varies between browsers. The most advanced implementations are in Chrome and obviously the new versions of Edge that are based on Chrome. But the gist of the way the APIs work is that websites are able to request payment via an API in the browser, and the browser actually invokes a wallet or a payment method that the user has previously installed into the browser. And that can take the form of a native application or another website. And what's quite exciting there is it's agnostic to payment methods. So payment via mobile money is one of the methods that we would love to see more widely supported. So Don's going to, there was a hackathon amongst the web payments working group about 6 weeks ago. Our colleagues from the GSMA very kindly joined us in that, and we put together sort of a proposal. We didn't manage to put any code together at the time, but a proposal of how you could use the browser APIs to complete an e-commerce payment, a payment in a browser where the actual flow of funds is mobile money. And so, following the hackathon, Don has spent the last little while putting this together, and he's got an end-to-end demonstration of exactly that. If there's any questions on the APIs, the payments APIs, feel free to get hold of me directly, or we can chat about them at the end.
Cool. Not sure if you guys can you guys see my this coffee screen?
Yes, we can.
Okay, cool. So firstly, if you guys all remember the Mojaloop app from last time, it's still around, but it's had some improvements added to it. So firstly, maybe just let me give you a little show of what's actually happening. So if you come to your mobile app, so this is your mobile money account, and as you can see, you can set up accounts and everything. What's new here is that now we add something called a service worker, which we'll go into a little bit details later. But what that unlocks now is that, like, let's say you come to this digital shop. So we've created this coffee.mojaloop.app, so somewhere where you can go to buy some coffee. And just to give you a taste of the experience that it unlocks is that now all you can do is just click a pay button, and then this little payment sheet pops up. And in the background, it communicates with your wallet and pulls some information about your accounts. So let's be good and take it from a shopping account, and you can click pay, and the payment goes through. So that's just what it will look like to the end user. So here in the actual ecosystem, this is actually what's happening. So at the bottom left, you have the user's cell phone or computer, and that's speaking to a user's mobile money operator, and which is connected to Mojaloop. And then on the other side, you have a merchant who also has its own mobile money operator account, and that's connected also to Mojaloop. So that's just the basic lay of the land. And obviously, because we're using the web, the user's cell phone and the merchant's website talk to each other over the web in the front channel. So yeah, that's just basically an explanation of the use case, which is what you just saw. So there are a few assumptions. So let's just break that down and go through them one by one. So firstly, as you saw, the user has to have a mobile money account on the app. And like I said, if you go to mojaloop.app, you can sign up for one. Just a reminder that this is the same app from the previous convening. So if you don't remember your password, please just use some other phone number. It just has to be a valid phone number format. Just use it as an identifier. Right. The second assumption is that the mobile money provider has implemented the GSMA API for the merchant payments use case. So this is exactly what we added to the module wallet. In our cases, we had to add two endpoints, the authorization codes and the transaction endpoints. You can go to developer.mobilemoney.api to see more. The third assumption is that the merchant needs to have onboarded to a mobile money operator, exactly like you saw. So it needs to be part of the same mobile money network. Okay, and then the fourth assumption is that the app is registered in the user's browser as a payment handler. So that's what you saw if you go to the little profile button there and you click install service worker. So just a quick note that currently this is only supported in Chrome and the latest Edge. So if you are trying to test this out, please be sure to use those browsers. And
it won't work in Chrome on iOS, unfortunately. Chrome on iOS is actually Google's wrapper around WebKit. It's not actually Chromium.
Oh, you guys are killing me.
Okay, so the fifth assumption is that the payment method that the merchant supports is defined by the mobile money platform. Okay, so this might be a specific list of DFSPs or an identifier for a scheme. So when you actually go to your wallet and you click that install service worker button, what it's actually asking the browser to do is register this payment instrument, and you can see there that the method, we've just named it Mojaloop.app because that's what our wallet is called. And then this is on what the merchant's website would call. So they would use a payment request, which is part of the web payments API. And this is the information that they would send in there. So this data part is not defined. This is sort of just what I've used for our demo. So I specify the amount, the currency, and this MISDN is actually the merchant's MISDN. So I decided to send it in there because that will allow you to do some lookups about the merchant, which you can get for free from the Mojaloop network, since again the merchant has been onboarded to that platform. So like you saw, once the merchant's website has called the payment request, a payment sheet is shown where it allows you to choose your account. So the payment app that you installed has already been authorized with a user's token. So that's how it's allowed to get access to the user's account. And as you saw, you can then choose your account to go forward with. The next thing it does is that it then calls out and gets an authorization code. It gets an authorization code from the module wallet. The mobile money API supports pre-approval. So you basically say, like, this is the amount that I want to pre-approve, and in exchange you get a code. If you don't want to pre-approve, there are other flows you can use that will get authorization through some other channels, which we can talk about later. So the payment app will then return this code to the merchant, and then the merchant can then request the transaction from its mobile money operator. So this is just an example of what that API surface looks like. You can see you can specify the debit party and the credit party, and obviously the type is now merchant pay. And then right at the bottom there, you can see the one-time code or the pre-authorization code that was generated earlier. Right, and then it gets fired off to Mojaloop, and then for those of you that are familiar, it uses just the transaction request flow. So you go through all the transaction requests, the quoting, and eventually the transfer. And then, so what I've done at the moment is that the merchant site will just poll its mobile money operators to see when the transaction's completed, and then that's how it is notified. So like I said earlier, there are some variations. The first one is user initiated. This can work directly from the user's wallet, which has been integrated with the user's mobile money account to initiate the mobile money payment via the API. And then the other one is the merchant initiated with out-of-band auth. So instead of getting a pre-authorization code, the user will just get prompted on either the app or SMS or USSD to authorize it. Cool. Just some learnings coming out of this is that there's a difference between a user and an account, and the current Mojaloop API doesn't clearly make that distinction. So it'll be quite interesting to integrate this work with what's going on the PISP stream, where they have that account linking phase. So looking forward to seeing what comes out there. Yeah, and that's it. Thanks.
Thanks, Don. Thanks, Adrian. Adrian, do you want to make a last comment?
Well, I think Don did a great job. One or two things maybe to point out, nuances that I think are important for people to recognize. Don, maybe if you bounce back a few slides, there was a nice screenshot of the payment sheet over the merchant page. Something to just note there is that those are two different websites. So this is one of the features of the payments APIs. As you can see, the merchant site is coffee.mojaloop.app and the other is mojaloop.app. Those could be completely different. So that could be, bobshardware.com and mojaloop.app. So the way we're thinking about this is that mojaloop.app is an example of a wallet that would be provided by a mobile money provider. And the merchant site, what's nice about this flow is that the wallet UI is rendered over the merchant site, so the user never loses context. It's hard to demo now, but it would be really great if anyone wants to try this on an Android phone. It's really an amazing user experience, because this payment sheet, the Mojaloop app piece, actually just pops up from the bottom of the phone, and it looks very slick. what you can also do, and this is something I think maybe for future work, is you can develop these apps as native apps for Android. So it'd be great to work with the PISP Stream guys to see if we can build this functionality into their demo app, so that what this flow would look like is you would be browsing the web, you would want to pay, the app would pop up, and you would actually authorize the payment using a fingerprint scan. So you would do, demonstrate all of the cool tech we've been working on all in one, all together. So I think that would be quite an exciting sort of end-to-end demonstration of all of this stuff coming together.
I would love to see that. In fact, that's the real case that I think really makes the third-party wallet make sense to people, I think, so that you don't have to have each individual bank try to figure this all out on their own. You have a master wallet that allows you to have that user experience across all your different account holding institutions and loans and credit and other things. So when you go to buy this cup of coffee, you might need to use credit to do it. I hope not, but if you did, you'd have the ability to draw on your credit line account through this PISP wallet. I was going to ask the question though, and it sounds like it's not doable today, that you can't show the Android experience, because of course a web browser on a desktop computer is one thing, but most people that we're targeting with this software will be either on a USSD phone or they're going to be on a smart,
so you can, if you go
smartphone.
and use the demo that Don's built now on an Android phone, it'll work, and it'll be quite impressive, I think. All the web-based stuff works fine on Android phone today. One thing I will point out, I don't know, Don, if you want to pop to that slide that shows the payment method identifier. One thing I wanted to just point out there is one of the, there we go. One of the challenges we have in the mobile money world is obviously, this is why we're all here, is interoperability. So, one of the easy things one of the things that's easy to do, at least when you're paying with a card online, is when you provide a card number, it's generally acceptable by everyone. Everyone's interconnected. And what this payment method identifier does is somewhat overcomes that interoperability challenge. It's not perfect, but it provides a mechanism to solve it at a different layer of the stack. And by that, I mean, if you're a merchant, let's say in a country that has multiple mobile money platforms that haven't come together yet, you can onboard with all of them, and you can call the payment request API once and specify all of the platforms on which you're onboarded, and the browser will pick the one that matches the app the user has installed, and it'll invoke that app. So, if you're in a country with, 3-4 different operators, and you as a merchant have got a merchant account with all of them, even if they aren't interoperable yet, you've had to do the interoperation work, but the user still has a great user experience. Any user from any of those operators who visits your site, when they hit pay, it's their wallet that gets invoked, and you interact with their wallet through that merchant integration.
Thanks, Adrian. Unfortunately, I'm going to have to cut it there and pass the session off to Henk and Rob to talk about TechOps. Thanks so much, Adrian and Don. Henk,
thanks,
Rob,
everyone.
Yes, I'm here.
All right, go for it.
Okay.
And we're going to be talking about portals, though, not TechOps. Well, I'm hoping we don't upset people by presenting on portals. Yeah, we've just for everyone's awareness, there's been a number of discussions, but Henk, you can move to the next slide. A lot of discussions on portals and how we should structure those. We've working with Mawali, and Mawali have donated their finance portal. Working with the guys from TIPS, we also have a clear view on the portals that we need to build. But as complexity starts building up through our various environments, we just wanted to basically create a framework that everyone can work to, but also then put some recommendations forwards of the challenges we're going to need to start looking at, particularly as we look at continuous growth versus deferred net settlement. Your finance portal needs to be configured differently. So first of all, we want to do is give a structure, and this is our first view. If people have got a different structure or a different view, then we're quite happy to take feedback on that and say, okay, what else do we need to consider? But a couple of things we need to look at is we need to make sure we're building something that's simple to use. We're guiding a user through completion of tasks. So task-based dashboards, clear steps if in long processes, easy collaboration. One of the things we need to look at is handing over from an authorization flow. But it's also going to be great looking. We'll come to that later. You know, this is the public face, but the challenge we all have to work through is how do we do this when some of us are building one product and others are building another element, but they all need to have the same user interface to actually support a user. So Henk, if you can move to the next slide. First of all, we want to just create this clear definition of there are different faces for Mojaloop. There are the customer facing, where only the customer will be doing things such as application or onboarding. Then we have an internal or external, or combined. So the finance portal would have a different view for different things. I'm going to go into more details as we go through to the next pages. But then also internal only, things that only the hub operator is going to need to look at. We've put some of the optional components in there as well, depending on the deployment and the mode that's being deployed. If we can move to the next slide, we'll go into more detail. So starting with the internal, so the very bottom of the stack and working up. Looking at how do I manage a DFSP? So we need a set of portals, because the user that's doing DFSP is likely to be very different to the person that's doing fraud, but maybe the same person that's doing operations. But again, as the operations and the opportunities of these services scale, that will change. So as you can see, we're starting to build a hierarchy of pages and different areas that we need to work through. Henk, if we can move to the next. Then the same for the customer facing, that onboarding. You only do it once, one hopes. As we mentioned, the virtual DFSPs, even then you'd hope that they would do it once. If they're sharding multiple virtual DFSPs to support one DFSP and they're scaling, I would hope they'd only apply once. But equally, a page where somebody can sign up needs to be there. Henk, if we can move to the more complex page, which is the internal and external. So in here, things like service management. How do I identify problems? How do I know that the service is up? If as a consumer I'm trying to send money and it's not working, why can't I go check a web page? The Dutch system of Ideal has a web page. A user can go in and see the state of any DFSP. I would want that same system health and availability. Oh, same page. System health and everything else visible to an end user. Finance, the finance portals need to be accessible by the DFSP. They want to see where their position is. If they're a small DFSP, they may not have the functionality to go onto the portal, check, see where they are. Reporting, auditing was raised earlier, but case and dispute management is definitely going to be needed between the DFSPs and between the hub. Then, of course, documentation. So these are the frameworks that we've put together. So if people have got views of different pages or different structures, please reach out to any one of us, Henk, myself, Joe, and Barreto are on the call as well, or any members of my team. These portals, we're trying to look at the framework that we look. So that's the first element. How do we create structure? Henk, if we can move to the next. So that's our first challenge, the framework. The next then is I'm signing in. One of the best user experiences I've had was actually for the European Bank of how you set up your users and different authentication models. So the hub has its registration, but a DFSP might want to assign multiple parties. If anybody's had the misfortune of working with Swift and their user interface, that's the comment on the user interface for how you set up your users. You have to know so much if you're using some of their tools. We need to learn from that and say, how do we create, makes it easy for the hub to manage their own authentication and controls for a portal that we work through. We then have a very simple navigation interface with common functionality and the ability to add new third-party add-ons. So we put into our picture the FXP. So as Motorsbox, we have the FXP, but that's an optional component we want to plug in. But you wouldn't need that module if you didn't need it. So that third-party add-ons functionality needs to be part of the thinking. Henk, if we can go to the next slide. So then I'm going to start handing over to Henk at this point. So this is where we start looking at what does that component design need to look like. But Henk, if you can pick up at this point. So we've hopefully for people, if that's created a clear view of the challenges, we'll come back to some more components in a moment. But Henk, for you.
Thank you, Rob. So this is basically just elaborated on a component diagram, just with a selection of those portals so that we can understand how the integration will work on a scale like this. So this is not everything, it's just a handful, just a selection, just to get a concept of that. So as a hub financial officer, you will obviously be authorized to actually access the system, and according to that, you'll be able to get an allocation for a specific role, whether you're supervisor or, sorry, just went off that one, whether you're supervisor or a capturer, those are essentially different people and different roles with different responsibilities. They would obviously then come into the system via the necessary security checks, the firewalls and so forth, and they'll be able to access the front for API, sorry, not the API, the UI, that is going to be the financial portal, maybe for the hub in this case, and he'll be able to access the API financial one and then interface into the Mojaloop backend. The same with the TFSP side as well. They've got a separate portal functionality over here that will interface into that, and via the common functionality, which is a shared code libraries, have the relevant access to perform their task, but they will not be able to perform any additional task or see anyone else's data from that perspective. And I think that's a trick as well, is how do you separate the authority and the segregation between a hub and the different DFSPs so that they don't have a view necessarily of the data or the security protocols that they are not allowed to see. Yeah, that's it on this slide. So then we move on to the next one, the framework. So some of the key considerations for that portal framework would be to have multiple implementations across a various amount of sites. It needs to be easy maintainable, and it needs to be reusable. So if we have a implementation at site 1, we want to be able to do exactly the same implementation at site 2, and just by literally configuring it, reusing most of that, and be flexible in our implementation, conform to that customer specific requirements, which brings us to customer centric configurable setup options. I mean, let's face it, the customer at the end of the day is the king, and you've got to really have his buy-in to make him look good and make sure that he is willing to use your product and be comfortable with that. So if you can't provide with it to him within reason for what he wants, then we've got a problem. But then he's going to sit with the application that he really does not want to use and really got no use for at the end of the day. Again, we get to the easy customization, accommodation for specific requirements and specifications. Obviously, within reason, some logic or some reason must prevail in all of that. White label capacity. We'll use the financial integration as one, where you would have a implementation A, implementation B, and you have the various type of settlements. And I think Rob touched on it before. I mean, you've got gross settlements versus multilateral net settlements. The functionality is different, therefore the user interface that they require is also going to be different. And you need to be flexible where you can allow certain portions of that to be visible, and other portions of that not be visible, because obviously that would not cater to those requirements, and the financial model that they might have chosen doesn't need to look exactly the same as between customer A and B. And then the best way to do this, or the ideal would to be able to use micro front ends within some of those portals, and you need to be careful there, because if you can use that with the ability to include or exclude certain things with the micro front end capabilities, and that gives it quite a bit of flexibility as well. That could complement the whole way that you go forward and you implement this from a frame of mind. The modular approach. That's something that we actually got stuck on, because if you can have a lot of different modulars that will be specific, task orientated, and be able to do something specific and only that specific thing, you can literally then take a whole web page and then plug in just those specific models that needs to be in that web page, and then ensure that that is the functionality that the customer wants, and thereby do that necessary customization. So a hub can be configured in one way and a DFSP can be configured on another way, and they can all use the same base code or shared common functionalities that there is. And I've mentioned this earlier. I mean, the use case that comes to mind is currently gross settlement versus multilateral net settlements. The way that those work and the requirements to actually display certain items on the screen is very, very different. You've got to be able to complement the business logic, be user specific on the contents, and obviously permission. Permission is a big thing. You need to separate roles where you would have a person that would capture something, and you would have a, let's say, supervisor that would be authorized to actually approve certain things and do certain admin functionalities on that physical interface onto the environment. From our investigation that we did and some research with the help of Ken's team and a couple of other people, we really believe that using the micro user interfaces, technologies, and applications, that we've identified a couple of candidates that we would really like to share with you that could actually fulfill into this. Like I said, there's a technology and the investigations. We basically went from a couple of heavyweight portals running on a server application versus an all front-end framework. Anyone that worked on the mainframe before, I think you run far away very quickly, and that's the same thing that we did here. We opted to rather look at the all front-end frameworks, as that is the majority of people is actually using it, and it's actually working well for a user interface, a lot better than some of these heavyweight portals that's running on a server application, as well as the fact that I don't really believe that we can at this stage justify to run some of those really big applications. And the requirement is just really not there. We surveyed a couple of WhatsApp clients, and we basically narrowed the approach down to a few candidates that basically conform to micro front-end framework and the different approaches for a customer and implementation that might be required. Okay. So this is the shortlist. I'm just going to take one big leap here, because otherwise we're going to be here for a couple of hours if we have to run through all of these options and discuss all of them. The frameworks we basically decided on to shortlist is Next.js, Luini, and the custom implementations would be native React and React workspaces. So that's just our shortlist that we looked at and that we identified. We quickly realized that React workspaces, even though it looks extremely good, when we actually started just investigating and trying to put a single sample page together, it was really not suitable for what we wanted to do, and it was really not what we wanted either. So we've disregarded that. Luini is a different character at all. You've got the ability to allow multiple front-end frameworks to coexist. Sadly, it requires iframes, which is a bit scary if you think of that. And the other thing that really counts against is the fact that you need specific API calls, and that's Luini specific. So integration-wise, you're going to have to do a lot of development and custom development specifically to accommodate a specific product. So the concept of plug and play is basically going to go out the window with that. Next.js, I think this is one of the things that we're actually quite excited about. If you look at what it can do, how it refreshes, and how it actually takes up new pages and the integration that we do. So that is why we're saying it remains a candidate in the mix for navigation and some other capabilities. It did not solve our core micro front-end composition problem. And that's the last point over here, which is really good. Webpack modulation federation, sorry. Tripping over my own words there. Especially with Webpack 5 coming up, I think it's this beta release that's just been released now. That became a very strong candidate for where we would like to go with this and where we see this heading to conform to the previous requirements that we listed out. So in closing, I think it's imperative. I mean, if you look at a portal or a user front end, that is the face of what you present to a customer. That's the stuff that people see every single day. So it's absolutely of high importance to put the best face forward for the product that these people will be working on. So as Mojaloop Foundation and these highly visible parts of a product, we really have to look really smart and sharp. with something that really works time and time again, and it's easy to navigate for these and easy to understand. Mojaloop Foundation also need to think about adopting a particular direction for these multiple implementation sites. That way we can actually put down a base code and core functionality down that could be shared and customized as you actually develop these in the different parts and different lines as we go along. The ultimate goal to further extend the reach of such high quality interface designs and efforts, it will reduce the technical overhead that we currently have, and it will maximize the resource productivity. So you don't have to have a developer sitting there and a designer sitting there, or a architect sitting there and looking at specific implementation and customizing it, where you have 20 variations of the truth. And then sadly, that will then increase the resource count, because these will then need to be maintained separately. And when you do new releases and the maybe a new API or interface, you'll have to change every single one of those. And that's the type of things we're trying to avoid. So how do we get these things to be a little bit more intelligent and maximize resource productivity to a better extent? I think, to sit there and spend 90% of your time to maintain something just to keep up with something that's being developed is not very productive. This recommendation is basically leaning towards adopting the approach of a modular and configurable and encourage highly flexible multi-site implementation that support reuse portal framework that we would recommend. And that's where we are at this stage. So at some stage, we would definitely love to present a proof of concept to you and see how all of these things work nicely together with multiple sites and multiple implementations.
Henk, this is really excellent. Thank you for bringing this forward. I'm very glad that you're looking at what I think the world is calling the serverless approach, or the all front end approach to this, because that was a growing concern of mine, that we were going to develop yet another server we had to maintain. That an implementer would have to also maintain, and if the monitoring server goes down, then your whole system is hosed. Whereas if you have a front end, lightweight front end stack orientation that uses an API integration to the core system, you can assemble any forms of different panes that need to look at the system for whatever reasons that they are, and they're separately maintained, separately implemented, and much lighter weight in the way that you would deploy them. So I definitely like that. I would have a quick look at jamstack.org if you haven't already. Jamstack is it's not even a thing. It's just a way of looking at serverless web development for 100 different reasons. This being one of those, but of course they're also looking at how would you replace WordPress, for instance, in a normal web page like environment. One of the things that comes out of that is the serverless concept itself applies to all these different cases, where you can do this front-end composition on a back-end tool, and then it deploys what is essentially a pre-compiled or pre-configured web page that includes all of the markup, JavaScript, and CSS that would be required to present that. And of course, it uses APIs for pulling data and interacting with the back-end systems. Obviously, in a cross-site scripting environment for public, that's challenging, but it's not challenging here for the implementation that you have, in that it's not really cross-site, although you can have multiple APIs that would be all considered. So Jamstack goes in, they've got one particular resource that's helpful, I think, which is about 100 or something different tools that all help with this particular aspect of serverless design, some of which Next.js is listed, of course, so as is so some of the React components, but you may find something else in there that triggers something for you to see where that goes. And I would love to see a proof of concept. Do you have any idea of what your next steps might be and how you would fit them into PI 11?
Yeah, that's a loaded question, Mother. I've got lots of ideas that we would like to do, but obviously we need to see what we are capable of doing and whether that's going to be in the right direction. I think you've actually summarized that very nicely. Jamstack, thank you very much for that recommendation. We will definitely have a look at that. That wasn't actually one of the technologies we even looked at this stage. Fortunately, I mean, being in a real development environment, you have to keep up with latest trends. I mean, we can't go and put an assembler or a COBOL front end. I mean, that's just not on. But
right, and just to be clear
Right.
too, Jamstack is not a platform or a foundation. It's actually it's a conceptual website that brings together these 100 different tools that might be considered under that sobriquet of serverless deployment. So it itself is not a platform. It's a way in which you can think about all these different tools through that one lens, which is very similar to what you're looking at here.
Absolutely. Yes, spot on. Yes, we're definitely going to have a look at that. Thanks, Miller.
Thanks, Henk. Thanks, Rob. I want to throw it back and see if you guys have any final comments as we transition to the next session. Henk, Rob. All right, cool. Thanks so much.
Thank you.
Yeah.
Thank you very much, everyone.
Thanks.